Let us now learn about Hooke's law and Young's modulus of elasticity. To do this, I am going to use this elastic rod. I have tied this rod at the top to the roof, and I am going to make a simplifying assumption that we can ignore the weight of this rod. Okay? When I don't apply any forces on the rod is in its natural length, right? So that natural length is L. If I now apply a force F downwards on the bottom face, then the top face, because it's connected to the roof is going to pull it, right? So the top face will have a force F applied by the roof, pulling it upwards. So you can see that these two forces, they are the deforming forces applied on the rod. Because of this, what will happen? Because of this, the rod is going to elongate. The rod is going to elongate. Okay? So you're going to have a strain in the rod, and the interatomic forces will produce a stress in the rod. So to understand the stress, let us think about a cross section. Let us say that the cross section area is A. So this cross section is going to split this part of the rod and this part of the rod like that, right? We can split it up like this. So this is the top portion of the rod. This is the bottom portion of the rod. The atoms that are here, they will pull on the atoms there downwards, and the atoms there will pull on the atoms here upwards. The total of all these forces is what we call as the restoring force. And because this rod is in equilibrium and we have ignored its weight, the restoring force there must be equal to F. Similarly, this restoring force must also be equal to F. Now, the stress that is developed in the rod, what is the formula for that? Restoring force divided by area. The restoring force is F. So we can write that the stress sigma is F by A, because the area of cross section is A. So restoring force F by the area of cross section A. This we already know. Now, because of these deforming forces, what is going to happen? This rod is going to elongate. By how much? By this much. Let us call that delta L. And so that means the strain that is developed in the rod, how much is that? Change in length by original length. So the strain epsilon is delta L by L. Delta L by L. Okay? Now the question that comes up is, are stress and strain connected in some way? Yes, think about it. If I exert a force F, let us say that the rod elongates by delta L. Suppose I double the force. What do you think? Obviously the elongation will also increase. In fact, you probably expect that if I double the force, the elongation will also double. But doubling the force means the stress has doubled, right? The area of cross section remains the same. So doubling the force means doubling the stress. And when you're doubling the stress, you're doubling the elongation, doubling the delta L. But L remains constant. So that means the strain has doubled. So doubling the stress means strain gets doubled. Robert Hooke studied this in great detail, and he came up with Hooke's law, which is stress is directly proportional to the strain. So doubling the stress doubles the strain. Tripling the stress triples the strain. A very good way to understand this is to draw the stress-strain graph. Okay? We can draw the stress on the y-axis and strain on the x-axis. So if we look at for different values of the strain, what is the value of stress, or for different values of stress, what is the value of strain, you'll see that as the stress increases, the strain will also increase. So the graph is going to look like this, and Hooke's law tells us it must be a straight line. But when you actually do experiments and find out what the graph looks like, it looks like a straight line for this part from O to A, and after that it starts to not be a straight line, right? You can see that curve. We will come back and study this stress-strain curve a lot more carefully. But what I'm interested in right now is you can see that this OA portion, that is the linear region. And Hooke's law is obviously not valid everywhere. It is valid only for this linear region. So this is where it is valid. Okay? And Hooke's law tells us that stress is directly proportional to strain. So what does that mean? Stress by strain must be a constant. stress by strain must be a constant. That is the meaning of this proportionality. Now this constant has a name. It is called Young's modulus and we use the symbol Y for it. So stress by strain is Young's modulus Y. By the way, all this is only valid for longitudinal stress and longitudinal strain, right? Either tensile or compression, doesn't matter. Basically, when we are talking about the stress and strain here, we are talking only about longitudinal stress and longitudinal strain. Okay, so stress by strain is Young's modulus Y. Okay, now let us think about it and rewrite this in the form of symbols. So for stress we use the symbol sigma and for strain we use the symbol epsilon. So sigma by epsilon, stress by strain is equal to Y, which is Young's modulus. And just remember that sigma is the longitudinal stress and epsilon is the longitudinal strain. Okay, so I hope you have understood this. Now the next question that comes up is, we know the unit for stress, right? SI unit for stress is, well, it is force by area, so newtons per meter square. That we know. We know the units for strain. Well, what are the units? It is delta L by L, which is meters by meters, which is actually dimensionless, right? So what will be the units for Young's modulus? Well, the SI unit for Young's modulus will be the SI unit for stress, which is newtons per meter square, divided by the SI units for strain, epsilon, which is dimensionless. So it will be newtons per meter square, right? Because dimensionless means nothing there, right? It's like, think of it as 1. So newtons per meter square, which is Pascal. So the SI unit of stress is Pascals, newtons per meter square. And the SI unit of Young's modulus is also Pascals, newtons per meter square. Because you are dividing by strain, which is just a ratio, right, of similar quantities, right? Basically, both of them are similar dimensions. So basically that epsilon has no dimension. And so Young's modulus, the units will be the same as the units for stress, newtons per meter square, Pascal. Okay. Now I hope you have understood this. I want you to now go back to this stress strain curve and let us think about any point that we pick up somewhere here. Suppose I pick a point there, it is going to tell you so much stress, which means if I draw a vertical line, that will tell me the stress, right? So if I start with this point, what is this length? This length is the value of the stress for that point. And what about this length? This length will be the value of the strain for that point. If I pick a point on this line anywhere, right, it has a stress value, it has a strain value. This is the stress value, this is the strain value. But stress by strain, isn't that the slope of this line? Yes. But stress by strain is Young's modulus. So Young's modulus is stress by strain, which is actually the slope of this line. You can pick any point on the linear region. You can go all the way up to A. You can pick this point, you can pick this point, you can go all the way there. Don't go beyond that. So if any point is given on this linear region, you can immediately find the slope of this line, and the slope of this line is equal to the Young's modulus. So whatever we call Young's modulus is nothing but the slope of this line here on the stress strain curve. Okay, so we have understood this. Now there are some very important points to keep in mind. Experiments show that for most materials, not all materials, most materials, particularly metals, whether the applied stress is tensile or compressive, it doesn't matter whether I'm pulling. Here I've shown you that we are pulling, but I could have also been pushing, right? So whether it is tensile or compressive, as long as the stress value, magnitude is the same, the magnitude of the strain that is produced is the same for most materials. That is, if I exert F and this area is A, right? Let us say it is delta L elongation, but suppose I reverse everything and I push it, right? So it is compressive. I'm going to now get the rod becoming smaller. So that's going to compress, but the compression length will also be the same delta L. So that means the strain magnitude will be the same. So for the same stress, if the strain magnitude is the same, that means the Young's modulus will be the same whether we are pulling or we are compressing, pushing, right? So Young's modulus Y is the same for most materials, not all materials. For most materials, it is the same whether the rod is in tension or it is in compression. What is Young's modulus? It is simply stress divided by strain, sigma by epsilon. But sometimes people like to say stress is F by A, so I should put F by A here. Strain is delta L by L. So basically F by A into the reciprocal of strain, which is L by delta L. So you can write this as F by A into L by delta L, or FL by A delta L. F into L in the numerator divided by A into delta L in the denominator. Now, I don't like to remember this formula. It is a lot easier to just simply say stress by strain. So, I'm going to always use from the basics that Young's modulus is stress by strain. Okay? Stress you can of course remember directly. It is restoring force by area, and strain is delta L by L. Let us now look at Young's modulus values for different materials that are given here. So, aluminium has a Young's modulus of 70 into 10 to the power of 9. SI units is newtons per meter square, which is pascals. So 70 into 10 power 9 pascals. Now 10 power 9 is a giga. So this is 70 gigapascals. Aluminium's Young's modulus is 70 gigapascals. Copper's Young's modulus value is 120 gigapascals. Iron is 190 gigapascals. You can see all of these are big values, right? Steel has one of the highest Young's modulus values, 200 gigapascals. Now, if you look at all of these, it is not written whether it is tensile or compressive. Whereas, when you come to bone, there are two different Young's modulus values. Why have I not given that for all of these? As I told you earlier, whether an object is in tension or compression, the Young's modulus value is the same for most materials. Not all materials, most materials, right? So, all these materials, the Young's modulus is the same whether it is under tension or compression. Whereas with bone, you have two different Young's modulus values. For tension, when the bone is being pulled, the Young's modulus is 16 gigapascals. But when you're trying to compress the bone, then its Young's modulus in that case is 9 gigapascals. Okay? Let us now see how to use these Young's modulus values in a question. By looking at this example, I have a steel rod of length 1 meter and cross-section area 0.5 centimeter square. Find the force that must be applied to elongate this rod by 0.1 millimeters. I'm going to make an assumption that we can ignore the weight of this rod. Okay, that's an assumption that we'll be making in most of the questions. So I'm going to make that assumption here. So what do we have? We have this steel rod. Let us say that it is tied to the roof there. It has a length 1 meter. If I want to elongate it, what should I do? Should I compress it or should I pull it? What do you think you should do? You must obviously pull it from both sides. This side anyway, it's basically being held by the roof. So the roof will exert the force. So I just need to exert a force downwards, right, at the bottom. So if I pull it with a force F, the roof will also pull it with a force F because I'm ignoring the weight, remember? And this is in equilibrium. And so this is going to elongate, right? How much should it elongate by? I want it to elongate by 0.1 millimeters. So delta L must be equal to 0.1 millimeters. That's what I want. Now, how much is the force that I'm applying? That is not given. That is the question. I want to find the force that I must apply so that this delta L is equal to 0.1 millimeters. The question is to find the force. Well, if I know the stress, I can find the force. I don't know the stress. But with delta L and L, what can I find? I can find the strain. I can find the strain. And then using the strain and Young's modulus value, that you know because steel, Young's modulus is given there, right? So using the Young's modulus value and the strain, I can find out the stress, and using the stress, I can find out the force. So that is the idea. So first, let us calculate what is the strain, delta L by L. So strain in this case is delta L by L, 0.1 millimeters by 1 meter. Convert millimeters to meters, 10 power minus 3. So 0.1 into 10 power minus 3, meter cancels. You're going to get 10 power minus 4. So strain epsilon is 10 power minus 4. Now using the strain here, I can find out what is the stress, because stress is strain into Young's modulus, or Young's modulus into strain, right? So stress is sigma, which is Young's modulus into strain. Now Young's modulus value I know, 200 into 10 to the power of 9. Strain value I know. So if I substitute that, 200 into 10 power 9 into 10 to the power of minus 4. Always use SI units. This is 10 power 5. That's going to give me 10 power 7. So 2 into 10 power 7 SI units newtons per meter square. So this is the stress. The question is not asking for stress. The question is asking for force. But once you know what is the stress value, force is just simply stress into area. So the force that we need, how much force F must you apply? Well, it is sigma into A. Now sigma, I know the value, 2 into 10 power 7. So 2 into 10 power 7, but what is area? 0.5 centimeter square, convert to meter square. So this is 2 into 10 power 7, that is sigma. 0.5 centimeter square to meter square is multiplied by 10 power minus 4. So if I now multiply this, 2 into 0.5 is 1. This is going to give me 10 power 3, 1000. So basically 1000 newtons. So how much force must I apply? You must apply 1000 newtons so that this rod extends by just 0.1 millimeters. Obviously this is a steel rod, right? So you must exert quite a lot of force. Now we can ask the question, suppose instead of a steel rod, everything is the same, exact same dimensions, but I use an aluminium rod. Suppose we used an aluminium rod, what will be the difference? Same length, same elongation I want, same area of cross section, but because it's aluminium, aluminium has a Young's modulus which is 70 gigapascals. So that means here alone I have to use 70 gigapascals. So strain value will be the same, epsilon will be the same, Y will change, area will be the same. Now let us see, this sigma is Y into epsilon. So if I put that here, it will be Y epsilon A. So you can actually write that the force required is Y into epsilon into A. Epsilon and A are the same as before. Y value alone is different. Y value is that value for aluminium. So if I substitute 70 into 10 power 9 for this, 10 power minus 4, and for area I'm going to use the same value that I've used before. So if I now multiply this, I'm going to get 315 newtons, 315 newtons. Notice that the force you need when you use an aluminium rod is much less than the force you need when you have a steel rod. So steel has a lot more Young's modulus, right? Much bigger Young's modulus compared to aluminium. That's why aluminium requires much less force, steel requires much more force. Okay, right? For the same dimensions. Now suppose I say, I don't want to use steel or aluminium. Let's say I want to use a bone. Right? I want to use a bone of length 1 meter, cross section area. Assume it is a uniform bone. Obviously bones are not uniform like this, but let us assume that. Then how much force will be required to elongate this bone by 0.1 millimeters? It will be the same formula like this, right? So the force required will be Y value for the bone into epsilon into A. But there are two values of Y. Which one should I use? Now think about it. You want to elongate the bone, right? So that means you must actually make the bone go into tension. That means you must be pulling. So obviously you are looking at the tensile value. So the Y value that you must use is 16 into 10 to the power of 9. The rest of the values are the same. So now when you multiply, you get 18 newtons. Much lesser than both aluminium as well as steel. So you can see that steel has such a huge Y value, and that means it requires a large force to produce a small elongation. So I hope you have understood how to use the Young's modulus values in questions like this.